Good morning, everyone. So it's a great pleasure to start today's session with the fourth lecture by Hugo.
Thank you very much for coming. So just before we truly start the session, let me give you the answers to yesterday's small exercises. So when you look, for instance, at the difference between spin-spin correlation in two graphs, and one graph is smaller than the other one, when you write that in terms of random currents, you get what? The first thing is here you are going to get W beta of N1 for currents on G. Divided by the same sum for currents in, let me maybe write it like that. Let's say H. The same sum without source for currents in H again. And here, because I want to be comparing it to the guy with condition on with graph G, I'm going to just do the same. I'm going to add a phantom, a shadow sum, where I just look, I add sourceless currents at the top and at the bottom, a second source. Okay. And now what do I do? Just I switch the sources from first current to second current, from the small graph to the big graph. I'm allowed to do that. The only thing I need to do is I need to add indicator that N1 plus N2 restricted to H belongs to FA. Okay, but now that A is on the second thing, if I forget the indicator function, I exactly get what I want. So this is smaller, so if I forget indicator, I get just sigma A G. Why? Because now the second current is in G, has sources A. I divide by the same sum with sourceless. This gives me sigma A G. And the first current has sourceless and sourceless. So in fact, I can just erase these two sums. So you see, it's very direct that you have the monotonicity. And the second one I wanted to explain, because this is an important inequality. So this sum, this Simon-Lib inequality, same thing, it's fairly easy to obtain. So what you do is you say, okay, sigma 0, sigma xg, it's the sum on currents with sources 0x divided by the sum on sourceless current of Wn1. Here the currents are on G. But now imagine I add, again, like here, I'm going to add a second current. Imagine I add a sourceless current, but on S only. So N2. So N2 belongs to N to the ES, sourceless. Okay, so I add a second current that lives only on the set S. Okay. So there is 0 and there is X. Notice that because 0 and X are sources of the first current, necessarily there must be a path from 0 to X in N1 plus N2 hat. Because there is already one in N1. There are two sources, there must be a path between the two. So that means that there must exist somewhere a point Y on the boundary, which is connected to 0 in S in N1 plus N2. So this here, as long as I put an inequality here, I can add here sum for Y on the boundary of S of indicator of N1 plus N2 restricted to S belongs to 0y, which just means this is just saying 0. This is just another way of saying 0 connected to y in n1 plus n2 at restricted to h. The same thing. Once you have that, you invert this, you put this sum here, and you notice that this is exactly what allows you to switch the sources 0y from, to make the symmetric difference with 0y. And you will get one source here. Now you will have y and x as sources, and there 0y. And this is exactly what gives you this product here. I will not put all the details, but you obtain it easily. Okay, so that was for the correction. So now let's start today's lecture. So as I mentioned repeatedly, the Gaussianity is related to this approximate Wick law. So today we are going to try to get it. So approximate Wick law and what we will call the tree diagram bound. Okay, so my goal today is to re-express using the random current and the switching lemma to see how we can compare sigma x1, sigma x2n, okay, and G2n x1 x2n. What is G2n x1 x2n is what you would get if it was Gaussian. So G2n x1 x2n is just sum of the pairings of the product of the I of sigma x by 2i minus 1 sigma x by 2i. Okay. So I want to compare these two things, and I'm going to focus on n equal 2. Okay, so when you have 4 points. You have to trust me that, in fact, well, I will actually give you the inequalities that allows you to go from n equal 2 to n equal, to general n. So for n equal 2, we have a special notation that I want you to know. It's called U4. And U4 is exactly sigma x1, sigma x4 minus U4, minus G4 of x1, x2. Okay, so it's exactly the quantity I'm interested in, the difference between the two, for n equal 2. Okay? It's called the Herschel function. Oh, yes, I promise that I will not be writing at the top, sorry. From now on, I'm doing it. Okay, so proposition. U4, I can re-express it as an intersection of currents property. So I claim that U4, and this is true on any graph. There is nothing special to our dimension 4 for now. I'm saying this is minus, it's equal to minus 2, sigma x1, sigma x2, sigma x3, sigma x4, times the probability. I'm going to tell you a little bit what this is. So probability x1, x2, probability x3, x4. So this is just, PA is just a measure that is sampling a current with sources A, and which is attributing probability proportional to the weight. Okay, so probability of n is going to be 0 if the sources of A is not equal to A, sources of n is not equal to A, and then it's proportional to W, so it's 1 over constant, and W of n if the sources of n is A. So it's just a way of sampling my current, and this is just a sign saying I'm taking the product measure. So here I'm sampling a first current N1 with sources X1, X2, a second current N2 with sources X3, X4, independently of each other. And what I'm looking at is are X1, X4 all connected? Okay. So all connected, sorry, I should say, maybe, in N1 plus N2 hat. Sorry. So I take the sum, I take the percolation process that I obtained from this, and I look whether all the points are connected. So notice that if I make a picture, I have X1, I have X2, X3, and X4. Automatically, because of the source constraint, since X1 and X2 are sources of the first current, there must be a path from X1 to X2 in N1. So a fortiori in the percolation obtained by N1 plus N2. Same thing, there must be a path going from X3 to X4. The question is whether these two, so of course, I mean, these paths, they are also, I mean, it's not only, it's not self-avoiding paths, right? It's, I mean, in a current, you may have some weird geometry. The question is whether there is a path between those guys and those guys. This is the difficult thing. And notice that the path is allowed to use if I keep the same color constraint, like the color code. The path could look like that, right? I mean, it could be just a necklace of going from N1 to N2 to N1 to N2, etc. So it's complex to see how you truly create a path between the first one and the second. Okay, so you see immediately that our game now, I'm going to prove that, but after we prove this proposition, our game will be to prove that in high dimension, in fact, typically, if I have these two currents, then X1, X1, X2, X3, X4 are not connected together. Okay, and we will make an analogy to random walk. But before that, I just prove this proposition. Okay, so let me do it like that. If I look at sigma xi, sigma xj, sigma xk, sigma xl, and I'm just x1, xj, xk, xl is just x1, x2, x3, x4. Okay? If I look at that, how does it compare to sigma x1, sigma x4 times the probability of something? I mean, okay, so when I look at that, and I write in terms of currents, I have two currents on the bottom which are sourceless, very good. And on the top, the first current has sources xi, xj, and the second has sources xk, xl, right? So I'm allowed to switch the sources from one current to the other one. So let's say I switch these two sources to the first current. The sources of the first current now will be xi, xj, xk, xl, so it's x1 to x4. And the second current will not have any sources anymore. The cost of that is that I need to add the indicator function that xk is connected to xl in N1 plus N2 hat. Okay? If I just play with this normalization and I use the definition here, you will therefore not be surprised to see that, in fact, what you are going to get is the following. It's like you can re-express it as a probability that xk is connected to xl in N1 plus N2 hat. That's what you will obtain when you write the switching lemma. This is a 4. Okay, so now when I jump here, so when I write this, and that I always express everything in terms of x1, sigma x1, sigma x4. So I have 1. This is just because I have this guy. And then here, I would have sigma x1, sigma x2 times sigma x3, sigma x4, sigma x1, sigma 3 times blah, blah. So every single time I'm going to take k, I mean, xk equal x1, and xl is going to go from 2 to 3. So here I'm going to get exactly minus, or if I write here, minus the probability here. Yeah, let's call it P, this. So P of x1 connected to x2 minus P of x1 connected to x3 minus P of x1 connected to x4. Right? I mean, here, I mean, x1 connected to x2 in n1% 2 hat, blah, 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 blah. But U4, sorry. Thank you. U4, which is this minus G4, sorry. Yes, thank you. So you get something like that. And here you notice that, in fact, this quantity, because of the source constraint, what are the possibilities? Either x1 is connected to x2, x3 is connected to x4, but they are not connected together. In this case, this whole quantity would be, I mean, okay, let me maybe do one more line. This would be clearer later. So here I could look at expectation of 1 minus indicator of x1 connected to x2 minus indicator of x1 connected to x3 minus indicator of x1 connected to x4. So now that I'm here, the source constraints tell you that anyway x1 is connected to x2. Okay? So either x1 is not connected to x3 and x4. In this case, this is 0. Or it is, but if it is, then it's these 3 indicators are 1, so I get minus 2. So the only 2 outcomes I can get from this random variable are 0 or minus 2. And it's exactly minus 2 if everybody is connected. And that gives me exactly this thing. So, by the way, sorry, at this stage, the source constraint is x1 connected to x4. So it's not necessary that x1 is connected to x2, but what is true is that either one of these indicator function is triggering or 0, or all of them, sorry. So I get this. X1 up to x4 all connected. And in fact, trust me here, if you redo one switching where you move x3, x4 to the second current, you don't pay anything. I mean, here, because they're all connected, you know that x3 is connected to x4. So you are allowed to switch the currents. And what you get when you switch the current is really exactly what I wrote as a. So this is just one more switching, and you get what you want. Okay? Yeah, so this is somehow the key observation. This goes back to Michael Eisenmann, and it's really a true equality. So in the literature and in what was done at the time, there were already some graphical representations of spin-spin correlations. Writing spin-spin correlation as sum of a, weighted sum of a path and things like that. In particular, there is a very famous one by Bridges, Fröhlich, and Spencer that allows you to indeed express even not just for Ising, but for other models. The difference with the random current expression is that the random current expression gives you exact equalities. The Bridges, Fröhlich, Spencer works usually gives you inequalities. So you manage to bounce, so sometimes it's sufficient, but here you get a true equality, and even if it doesn't play an essential role for dimension 5 and more, it will play a very important role in dimension 4, the fact that we have exactly an equality. Okay? And this is something specific to Ising in some sense. I mean, to Ising, to the Ising universality class, I should say, to be more precise. Okay. So when you see that, it starts to be good because you have clearly an analogy that starts to build up. So the analogy is the following. So, well, maybe I don't redraw. No, I redraw. So I have my 4 points. And I know that there is a path from 1 to the other, and another path from the third one to the fourth one. Forget for now that there are many loops and things like that, or directly think of the clusters of each one of the two pairs. So the analogy is the following, that we are looking whether they intersect or not. And if you do the same reasoning with random walks, you take just random walk starting from one point going to another point, I mean, condition on hitting this point, a random walk here, condition on hitting this point. And let's say that the distance between the points is order L, okay? Then when you do that, so 4 random walks, you have something happening at dimension 4. So for D larger than 4, then the probability for random walk, I'm going to put random walk like that, just that they all intersect, it does tend to 0. And in fact, it's even simple. The expected number of intersection is actually tending to 0. So if you look at the expected number of intersection, let's say, so you are looking, for instance, you sum over y, the probability is that both walks go through y, you get the green function between this and this, times green function between this and this, times green function between this and this, and green function between this and this. And when you sum over y, you get something tending to 0 as L to the 1 over L to the d minus 4. So it's a very easy thing that this thing is big O of L to the 4 minus d. And this you can even get by expected, just bounded probability, expectation, bounding the probability of intersecting by the expected number of intersection. And there it's very easy to estimate. Okay? In dimension smaller or equal to 3, then this probability, it's also very well known that it's larger than constant. It doesn't decay when L goes to infinity. Okay? And in dimension 4, well, in dimension 4, if you do the expectation computation, you see that you get big O of 1. So the expected number of intersection is of order 1. It's something very easy to get. But the important thing is that in the random walk picture, if you have an intersection, then, so conditionally on having an intersection, then you have many. So the fact that you have order 1 expectation, in fact, tells you that you have probability tending to 0 of intersecting, because condition on having intersection, you have many. Okay? So here, again, this thing, in fact, in this case, is 1 over log. But I want to insist on the fact that it's 1 over log, but the expectation is order 1. Okay? And this is going to be exactly reminiscent of the difficulties we are going to be facing. So we are going to face exactly the same. So now what do we do? In this lecture, what I'm going to do is I'm going to kind of rephrase or bound this quantity in a way that we kind of see exactly the expectation of the number of intersections appear naturally. And that will be sufficient to conclude for D larger than 4 strictly. Exactly because exactly like for random walk, the expected number of intersections will be small. And I will, I think, state, if I have time, I will state an improvement on this bound that just consists in looking at the expectation, which we will have to prove tomorrow. And that's this improvement that will allow us to go to dimension 4. And what we will have to do is to prove basically that if there is intersection, then in fact, there are many. Okay, so let's go to the improvement on this estimate, so proposition, it's called the tree diagram bond. And the tree diagram bound is saying the following: U4 is bounded by twice sum over every y of sigma x1, I mean sigma y, sigma x1, sigma y, sigma x4. So very elegant estimate, and it's called the tree diagram bound because physically some people will actually interpret it like that. It's like you are summing over y, this kind of diagram where you put a line if you are putting a sigma a correlation between them. So you are summing over y all the points. And I'm not fully going to prove this. I'm going to give you an idea of the proof, but there is just one correlation inequality I don't really want to be doing because by experience, people don't like it so much. So here is the inequality that, I mean, the correlation inequality that I'm not going to really prove. So the probability is that you are all connected. Okay, so which you can write, maybe let me write it like that. You can write as the cluster of N1 plus N2 of X1. So this is the connected component of X1 in N1 plus N2. Intersects the connected component of X3 in N1 plus N2. Okay. So this I claim, and it's not difficult to check, but it's not super intuitive, but I claim that it's smaller than the probability if you take, I mean, I'm decoupling basically here. I don't like that I have N1 plus N2 and N1 plus N2. I would like to have disjoint currents. And in fact, it's just not difficult to check that you can take 4 currents. And then the advantage of that is that you can look at the intersection of the cluster of X1 in N1 plus N2 with the cluster of X3 in N3 plus N4. And really here, I'm not hiding something. So it's even on a picture, you can see it. But my experience is that if I do the computation, people get lost. And if I do the heuristic explanation, I get lost. So, I mean, in both cases, we are losing. So there is a monotonicity like that. It's not that surprising because here you are putting more and more currents in some sense. So it's, I mean, clearly it's even simpler to intersect. But you have to turn it into something rigorous. So trust me on this one. But once you have that, it becomes much simpler because, so U4 in this case is therefore smaller than -2 sigma x1, sigma x2, sigma x3, sigma x4. So let's say if I want to bound U4 in absolute value, then I remove the 2. And then here, instead of putting this probability, I put the second one. And what I'm going to do here is I'm exactly going to do what I promised, I mean, people would be doing with random walk in high dimension. I'm going to bound the probability of intersection by the expected number of intersections. So here, I'm going to say sum for y in ZD. And here, I'm going to say, OK, so I want y to belong to the cluster of N1 plus N2. Y belongs to N1 plus N2, cluster of X1, and Y belong to the cluster of X3 in N3 plus N4. right? And here I just split because these two guys are actually independent, right? I'm sampling each one of the currents at random, so these two currents are independent of these two, so these are two independent random variables. So that's why I wanted, in some sense, to introduce these new currents, is to have random variables that are independent. Let me keep this one. Okay. Let's look at this guy, for instance. So this is, I'm summing over currents. At the numerator, I have currents with sources x1, x2, and second current with no sources, but I know that y is connected to x1, the sum of the two sources. So what am I allowed to do? It's easy when you have only one trick, you are certain to get it right. So you can do the switching lemma. When you switch the lemma, you are going to switch sources y, x1. So you are going to have for the first current sources y and x2, and for the second sources y and x1. So when you do that and you are careful that here it's not the sum divided by sum with empty set, it's, you see the renormalization, the partition function of this measure is the sum of the currents with sources x1, x2. So when you just take this into account, what you obtain is, so let me write it like that. So what you obtain for this quantity, and it's an equality, is you obtain this. This is reminiscent of the fact that after switching, you have sources x1y and yx2. But just beware of the fact that here it's a probability measure, so there is a partition function. So in fact, when you do things properly, you end up with a renormalization like that. But it's really just a switching lemma. It's the same as the one you see in the simple case. And you do the same for the second term. And you obtain this. And now you just simplify and you get what you want. Okay? So the tree diagram bound is nothing, I mean, you obtain it from the equality there by just doing this, I mean, decoupling the two currents, and this requires a tiny bit of work. And then you just bound probability of intersection by expected number of intersections. Okay. Good. Before I start bounding really these guys, let me just mention, because you may be worried that I'm basically focusing on the 4-point and that there is something special about the 4-point. In particular, I mean, you could really be worried because in the 4-point, there is one thing which is very good, is that I have 4 points. In the sense that here, when I take product, I have only two currents, and notice that every time I'm switching thing, I'm switching between two currents. If I look at n larger than 2, so if I look at 6 points or 8 points or something like that, naturally, when I'm going to look at the product of my pairs, I'm going to have I'm going to have n currents. And in fact, the switching lemma doesn't work well with n currents. It's really with 2 that it works well. You get equalities only with 2. But we are saved by the fact that you don't need, in fact, and this is something that was actually observed. I'm going to even write it here, even by Newman first. But what I'm going to state here is due to Eisenmann. So Newman didn't state this proposition, but what he stated is, is implying that, is as strong as the proposition I'm going to mention. So Newman noticed that if you want to prove that something is Gaussian, in some sense, you only need, when you have Lie-Yang, which is the case of the Ising model, then you only need to look at the fact that the 4-point function satisfies the approximate Victor. As soon as the 4-point function does, in fact, the 2 n-point function do. Okay, it's a very strong, very cool result. It's based on Lie-Yang. Here, I'm going to use directly random current, and this was an observation by Michael Eisenmann. And the observation is the following, is that when I look at sigma x1, sigma x2n, one thing is that it's bounded by G2n, by the Gaussian thing. And this is, you can see it fairly easily with random currents. And the other thing is that from below, you can also bound it by G2n. It just, you need to subtract something. And the something is the following. You sum over xi, xj, xk, xl. So now notice that you have two endpoints. So what I'm saying is that, you sum over I, j, k, l. So you choose 4 indexes. And what you do is you put G2n minus 4 of x1, xi hat, xl hat, x2n. So meaning you look at the Gaussian part when you remove the 4 points, okay? And you just look at U4 of xi, xj, xk, xl. You have a cool bound like that. And here it's absolute value. You have a bound like that, but this bound is telling you something very useful, is that if you manage to prove that U4 is much smaller than what you expect, if it was not Gaussian, so if you manage for the 4 point to prove that this is quite small, then in fact you get it immediately for the, you get immediately that this minus this is small because this is of the right order. So if this is smaller than the order you expect, you actually get that this whole sum is smaller than the order you expect. And this inequality, you can obtain it by the random current. It's just a little bit technical, but it's not long. But it's definitely not something I would enjoy doing on the board. And if I don't enjoy, you will not enjoy. Okay? But the bottom line of this proposition is that dealing with the 4 points is not only just a pedagogical choice, it's actually sufficient. Okay? And this is something very general. Okay. So let me just do the computation for, let me prove, so theorem. So this is maybe 4.2, proof of triviality. For D larger than 4. And here, strictly larger. Here, I'm going to make an assumption. It's not a big, I mean, it's a very big assumption, but you can actually run the proof without it. It's just that it's much more ugly. So from now on, and this will also be true for tomorrow, I'm going to assume that sigma x, sigma y, beta c, is behaving up to universal constant like a power. And this power, for reason that will become clear later, I write it as d minus 2 plus theta. It's not easy to prove. Even in dimension 4, I think we only understood this very recently. So it's not very easy, but let's make this assumption. And the first remark I want to be making, which actually allows you to do the thing without this assumption, is that for the Ising model and for many statistical physics models, reflection positivity, which is some property of this model, reflection positivity, it implies the following. It implies that, that's what I mentioned, I think, earlier already. It implies this bound. It implies the bound where you bound the spin by the green function. So in particular, it tells you, and this is important here, it tells you that eta is larger or equal to 0 because of this reflection positivity. In fact, everything works just using that. And this is rigorous. But it's a little bit more tedious, so I don't want to do it. in this context. Okay, so if we make our assumption, what do we get? So let's focus on the case which is really sufficient, the case where the points are at mutual distance which are comparable. It's true that you could take 2 points closer than others, just gonna be, so let's take x1, x4 at the mutual distance. Of order L. Okay? So sigma x1, sigma x4, or I mean, let's say sigma x1, sigma x2, sigma x3, sigma x4, for instance. This is of order what? Well, it's of order 1 over L to the 2d minus 2 plus theta. So my goal is to prove that U4 is much smaller than that, right? It's one of the guys in the difference in U4. So if I prove that U4 is much smaller, it will in particular tell me that sigma x1, sigma x4 in the same correlation is of this order as well. So it will tell me that indeed U4, I mean, the difference is much smaller than the actual order. Or if you want, I mean, Griffiths is also, right? I mean, by Griffiths, you also get this. Bigger, larger than this. The product of correlations is smaller than the correlation of the product. So I want now to bound U4. And if I just take the tree diagram bound, I get that U4 is more than twice. I mean, it's big O of the sum for y of 1 over x1 minus y to the d minus 2, 1 over plus theta, 1 over x4 minus y to the d minus 2 plus theta, right? And this, if you sum over every y, you immediately get that this is 1 over L to the 2d minus 2 plus theta. That's what you wanted. But what you further get is a 1 over L to the d minus 4, and you get a plus 2 eta in this case. But the important thing is that whatever eta larger or equal to 0, you get the order you were looking for times something that is going to 0. Okay? This is just like just you sum over every y. So this tells you that U4 is smaller than is big O of sigma x1, sigma x4 times 1 over L to the d minus 4 plus 2 eta. But this is good. I mean, I didn't tell you what D is right now, right? So in particular, it tells you immediately, so for D strictly larger than 4, we are done. Since eta is larger or equal to 0, we are always getting something much smaller than the spin spin. For D equal 4, we may also be done if we are lucky, meaning we are done if eta is strictly positive. Done if eta is strictly positive. And this was observed already in the paper of Eisenmann and Fröhlich. I mean, in the paper of Eisenmann and in the paper of Fröhlich. It was observed that indeed, if you look at dimension 4, and if the eta is strictly positive, in fact, if this is little o of 1 over this, if it's little o of green function, it's even sufficient. You don't need much. Then you get triviality. The big problem with this observation in terms of scientific interest for us, like for the question, is that it's not expected to be true. In dimension 4, we do expect So careful. For d equal 4, we predict, I mean, not myself, but everybody predicts that sigma x, sigma y is of the order of 1 over distance to the d minus 2. So you cannot use just this bound to get you away from what you expect to be happening in dimension 4. Okay. So again, at this stage, you have to fill the gaps, but this bound, the fact that the ratio is small, is sufficient to tell you that the ratio between G2n and sigma 1, sigma 2n is very close to 1, and this is sufficient to give you Gaussianity. At this stage, I didn't fully prove triviality in dimension 4 and more because I use this assumption. This is really an hypothesis. But notice one thing at least, that if you have this bound like that, it's in the right direction to tell you that you don't have intersections, right? Because when you look just at U4, here you will still get this bound. The problem is that it's not easy to re-put this guy in. Because this, the sigma 1, so if you don't have this thing here, then you cannot say, I mean, this estimate here doesn't give you an estimate on the ratio. So you have to work more to kind of keep, in some sense, the estimate on the spin for at least 2 of the 4 guys you have in the, I mean, you notice here that you have 4 spin correlation. By being a little bit smart, you can keep 2 of them and work, and you manage to get the triviality out of that, but it requires a little bit of work. But the moral, at least, is encompassed in what I said. I have 2 minutes and, okay, let me state, it's more, I will restate it at the beginning of tomorrow, but so I'm going to call it already Sync 5.1, so improved infrared band, improved tree diagram band. So what is going to be the game tomorrow? The game is going to be to prove the following. So for now, I'm just writing it. So I want to bound U4 again. There is going to be again a sum over y of sigma x1, sigma y, sigma x4, sigma y. But I want to improve on that. And I'm going to get a bound where here I'm going to get a new quantity, BL of beta to a power C, where BL of beta C is called the bubble diagram. So it's a sum for every Z of sigma 0, sigma Z squared. Okay? And it's Z in the box of size L, where L is the mutual distance. L is the mutual distance between the xi. So you see, if I forget that, I exactly get the infrared bound. But I'm going to add this thing. So this thing, adding this thing is completely useless in dimension 5 and more. Why? Because if you look at this here, if you plug the bound here, you see that it's finite. So the bubble diagram in dimension 5 and more is finite. So you don't gain anything. Just you got, I mean, it's different constant, but you get exactly the same. But in dimension 4, notice that if you plug, so you agree that we want to be looking at the eta equals 0 case, which is the remaining case. If you plug in dimension 4 and you sum on all the points in the box of size L, what do you get? You get log L. So in the bad case where the spin-spin correlation behaves like the Green function, then the bubble diagram blows up logarithmically in the size on which you are summing. So this will tell us that if we are unlucky in some sense and we are almost of the order of the, we are exactly of the order of the Green function, then this improvement is telling me that we get a log here. And this improvement is exactly going to be, in some sense, no, pause. Or I would be very bad in a movie with a bomb. I can tell you that. Yeah, okay, I'm dead. So this guy will come exactly from the fact that condition on intersection, in fact, I do re-intersect several times. And that's what I'm going to need to justify to you tomorrow, is that condition on intersection for this path, you re-intersect. It's exactly what happened for random walk. I need to prove it for random currents, which are very non-Markovian path in some sense. So it's kind of imagining proving something for random walk, but you have to prove it for self-avoiding walk, something like that. And that's what we will do tomorrow. I mean, at least I will try to give you an idea. Thank you very much.
We can take a few questions.
Yes, so for this strictly larger than 4, there was a small loophole in the literature, it seems, that everybody believed that it was proved. So it's proved when you use less expansion in very high dimension. That is true. The upper bound is proved by infrared band, but up to, I mean, we had discussion with Michael. I mean, I don't think it was proved anywhere that you had the other inequality. So in some sense, the idea that you had triviality, so you were Gaussian, I think just everybody then thought, and even like the author of that it was easy to get the lower bound, and in fact, to get that you have Gaussian free field, because you see, I mean, you have a trivial, I mean, you have a Gaussian process. If you manage to prove that this behaves like the Green function, then you end up with Gaussian free field. You even describe the Gaussian process itself. You have the covariance. So it's very interesting to actually get this estimate with zeta equals 0. But I mean, to the best of my knowledge, this was not appearing anywhere, and it's not easy. So when you can do renormalization, it's done. When you can do less expansion, it's done. But there are cases, the nearest neighbor model in dimension 5, where you cannot do any of the two. So actually, with a student in Geneva, we observed that you can do the inequality. There is a random current can allow you to prove the inequality. But I mean, we didn't write this yet. It's on our plate. But... So in the earlier proof, this was used and only this. Okay. So in dimension 4, I'm not going to use this. I mean, in the paper, I'm not using this hypothesis. I mean, we are not using this hypothesis. We present it under this hypothesis first because it's much clearer what happens. But then we managed to do it without the hypothesis. And that was the same in dimension 5 and more. They knew how to do it without this hypothesis. So this is purely pedagogical. But you don't need this hypothesis to prove that you are Gaussian. To prove that you are a Gaussian free field, that you would need. And this is dimension 5 and more. I claim that we are probably able to do it, and probably because it's not written on the archive. So I don't want to commit too much. And in dimension 4, it's a big challenge, but maybe it's not impossible. But it's almost a different question, in fact. It's kind of identifying the.
Any other questions? If not, let's thank Hugo again.
Thank you very much.